Those Space People, a podcast series of casual cosmic conversations with people working on exciting space projects.
Today we have Surya Kiran Peravali with us. He has a background in aerospace engineering and he's currently a research fellow at DESI in Hamburg. Hi Surya, welcome to the podcast.
Thank you, Rachna, for inviting me. I have been already binging on your show for past 1 year and really great admirer of your show. And today you invite me for the show, and I feel really special.
That's awesome. Thank you so much. Can you talk about your current research work at DESI?
My current research work is like an amalgamation between different things. My background is in fluid mechanics, and I work on fluid mechanics with rarefied gas flows. Also, I work with multi-scale methods, which is like coupling this fluid mechanics with particle physics, and also like I had to work with this high performance computing. Like I create different codes to simulate these phenomena, and also like I had to improve the performance of this code so that to have an optimal performance of this code.
So, for me, what's really interesting is you have a background in aerospace engineering and you are doing your current research work at DESI, which is a particle research. So, how can you talk about your journey, like after your bachelor's in aerospace engineering, what all happened and what led you to working in DESI and your current research at DESI?
So I have my bachelor's degree in aerospace engineering in India, and later I moved to Europe for pursuing my master's in computational mechanics, which is focused mostly in computational mechanics, like structural engineering and fluid mechanics engineering, and all the things. So we have one challenge being an aerospace engineer because all these kind of sophisticated technologies we need, and with an Indian passport, it's hard to find a really good research project to pursue our research. So what I did was like I have used these aerospace concepts to in other industries. Like I got an opportunity to work with marine industry. Like in aerospace, we are properly trained to work with this propellers and how we can design these propellers and how we can make these performance characteristics of these propellers. So I applied the same theories in marine industry. So even ships and submarines also have these propellers and similar kind of aerodynamic design. So I was working with a lot in marine industry, and also did and further then I moved to multi-phase flows. So in this marine industry, there is an interesting phenomena which I found called cavitation, which is like where the fluid changes its phase, and we have to include this in our simulation codes. And so I worked in this multi-phase flows for several years as in a European project. Um, in multi-phase flows, and later I joined another project, like because I'm exploring different methods how to deal with this fluid phenomena, and I found one interesting method called smooth particle hydrodynamics. So I would like to explore more in this smooth particle hydrodynamics, and what is the best way to do is like to take up a project. So I took up a project which is like simulating blood flow inside a human body. So um, I was coupling this, I was doing like several multi-scale simulation approach there in that project, uh, and later the similar phenomena is applied in particle physics also, like because this rarefied fluid mechanics, the fluid goes from subsonic speed to supersonic speeds, and this same kind of phenomenon is observed in our rocket propulsion, and also this fluid moves at different regimes, like from a high pressure regime to a very ultra high vacuum regime. So where do you find this vacuum? It's in space. So it's a similar physics which I'm applying, but on a different scale and industry.
That's very interesting. You talked about two different projects, but let's break down these two, right? So, first, you talked about your research work at this ship testing, the Swedish ship testing facility. So, what is it? What is the end result of your research? So, So you said that you were trying, you were working on aspects such as cavitation and improving several other aspects of, I don't know, how to increase the efficiency of testing ships. But what exactly is the end result? Do you make it faster? Do you make it easier? Does it make it much, is it a more exhaustive form of testing? So what's the end goal of your research?
My end goal of my research is like basically let me say what we do in this testing institute. Like we scale this, we test this ship models and all these marine bodies in a model scale because we can't test it in a full scale, obviously. So we use these results and apply some empirical formulas to predict the performance of the ships and everything in a actual full scale. So at that point when I'm pursuing my research, the challenge was to there are like a new kind of unconventional propellers in the market. um, and like traditional propellers have this scaling formula already, like they tested for like several years, but this particular scaling formula fails for new kind of propellers. So my research is to uh, study these propellers and try to study this formula of the scaling. And so I did model scale simulations and also did like full scale simulations of these propellers. And I correlated with this formula and proposed few corrections for this formula so that the same formula can be applied for new designs as well.
What kind of backgrounds did your colleagues or other researchers working with you alongside in this project come from?
Most of the people come from either civil engineering, mechanical engineering, and yeah, aerospace engineering like me. And there are some naval architects who are like more studied the core of hydrodynamics, and they are quite experienced with ship design and everything.
And then the second project you mentioned about modeling the flood flow. So is it common for aerospace engineers or people with degrees in aerospace engineering to get into this kind of work? Because for me, it seems like the medical sciences apparently seems to be quite far away from aerospace engineering. So is it very common for people with your background to end up doing this kind of research in the medical field?
I mean, I would say like being an aerospace engineer means like we are experts. We are exposed to the sophisticated kind of mechanics. What we do is like a mechanical, the basic engineering, but we do it at the highest level. So that means that we can apply this to anywhere. And being an aerospace engineer, we are like trained to do this fluid mechanics and all this computational stuff. And Yeah, it's just like a change of an application. We change the regular air to blood. That's it. And Of course, there are some challenges there as well because being blood being a non-Newtonian fluid, so it has different rheological properties and it's flowing inside a human beings. It's not like that could be tested. There are some ethical. And Another thing is like we can't test like how we do it in aerospace engineering or any other industry because here we have to do ethical experiments. We can't test all these things in random human beings, right? So simulation is there is a really huge need of these simulation engineers and everything. So suppose yeah, it's just to be like really good in your concepts so you can apply it anywhere.
That's very good to hear. This is exactly like spin-offs, right? We only hear of technology spin-offs, but this is like human resources spin-off from space to other industries. That's great. That's so nice. So coming back to your research at DESI, is it how related is it? Because to me it seems like your past research, be it at the Swedish ship testing facility or the research, the medical research, and your DESI research, how are they connected or not connected? How are they different? Can you contrast these?
I would say like for example, let's take this simulation of this blood flow. It's not like just simulating this blood flow because even before I started this project, there are like several models for blood flow, like people simulated blood flow. So it is quite yeah, easy. But the major challenge is to simulate what called these endothelial cells which are flowing inside the blood. So for that I had to couple this multi-scale like I had to use a tool which couples this multi-scale method with fluid mechanics. So similar thing is applied here, but at a different scale, much because endothelial cells are in the range of micrometers, and where the particles which are studied at DAISY were like ranges from micrometers to even nanometers or even much smaller than that. So of course it's more complicated than the previous project, but yeah, and moreover, like blood flow is completely laminar and no turbulence and other kind of chaotic theories. But here there could be turbulence, there could be like the fluid is compressible, and yeah, there are several factors like that.
So essentially, the underlying theme would be fluid dynamics.
Yes.
Okay, so anyone who has a background in fluid dynamics can work, could have worked in any of these areas.
Yes, you need to have a background in fluid mechanics, and also you need to be really good programmer, and also you need to understand the physics, basically, what how it is interacting, and what are the forces which are responsible for this, like how this particle are interacting and everything. So
Yeah, yeah. So a little bit of domain knowledge, essentially.
yes.
DESI, I assume, is a very physics heavy research that happens. So did you have to take any physics related courses, or did you even for your other work, your other research areas? All these three are like so different. Did you have to take any additional courses, or did you just learn all the basics on the go?
One major thing is to communicate with this other experimentalists and everything, like what's happening. And yeah, I do a lot of networking to fill my knowledge gaps. There are some several trainings happening at DAISY also, so which we can improve ourselves. So whenever there is a seminar on this one, every week there could be some seminar and a random seminar happening. So we could we can join and we can, yeah, learn ourselves.
Okay, interesting. So maybe can we talk a little bit about DESI, because DESI, as you said, is a physics a particle research lab. But outside of the physics community, the only lab of this kind which people know outside of the physics community is the Large Hadron Collider, CERN in Switzerland. So what is DESI? Like, how long have they been doing this research? What kind of research did they do, and how is it different from CERN or other particle colliders? Can you talk about DESI research in general?
Yeah, every particle research lab has like several entities. They won't just do like this large LHC kind of experiments. So they have like different entities. Even LH, even the CERN has like different entities. For example, like World Wide Web was founded in CERN. Yeah, they do, and all these experiments they spend like billions of dollars, and so there are many people who have a background in this finance and everything work at such labs. And also like uh, they do a lot of x-ray related stuff, so which could be applied in again medical field and space field and everything. So it's like a combination of different fields. And DAISY is also like a similar kind of lab, but not like as big as CERN. But yeah, it is also having different colliders, and they do the similar kind of. They have really good facilities that could at least read the experiments from LHC and everything. So yeah, there are several labs. Like one of the thing is like a Fermi lab in USA. There is ESRF in France, and there is now DESI in Hamburg. So
Also, you've mentioned to work in different kinds of these projects, you should be essentially know the basics of fluid mechanics and have a little bit of domain knowledge. And you also mentioned that one should be a good programmer.
yes.
Can you talk about what kind of programming languages you use? And I'm assuming it's not really general practice, or at least it wasn't common practice when I was doing my undergrad to learn programming, unless you are, doing these computer science or very software related courses. I've none of my friends who studied aerospace engineering have learned any kind of programming languages in their undergrad. So how do you see this trend changing? Because now you see researchers everywhere, irrespective of their field, learning at least Python or some kind of a scripting language to process their data, to make sense of their research and make things better for every day for everybody. So how do you see, like, when did you start learning programming languages? Which programming languages do you use? And do you see this trend changing? Do you think more and more people from non computer science backgrounds are learning programming languages now? And yeah, can we talk about that?
Yes, sure. Because I started my programming when I was doing my bachelor's degree itself. Because I was working with this computational fluid dynamics, and I was initially using these commercial tools. And these commercial tools, we use this student license to do some small projects and everything. And sometimes these licenses often there is a restriction to carry on, like take our research to a much higher level. I mean, for example, I have to use more computational resources for my bachelor thesis, and what the company says is to buy a new license or change your license from student license to commercial license, and we are not in a position to pay a lot of money for that. So then what I found was like to have I mean, I was motivated to build a tool which is like open source and everything. So I started my programming initially with MATLAB, a simple yeah. So I built my first CFD code in MATLAB, and then after coming to Europe, like I was exposed to different tools. Like already people are doing this open source, building up this open source tools, and then I started joining my professor's research, who is also working much in this open building up this open source. So then I had to shift from MATLAB and Fortran to C++ all of a sudden, because the open source code is written in C++. So then I have to do that project, and also this a project in Ship Testing Institute. I was using the same open source tool, and then I yeah, slowly. I mean, when we take up a project, we automatically learn it, right? So we explore different repositories, and we study different codes, and yeah, that's how I learned programming. And for for post processing again, I use Python to make some beautiful graphics and everything. uh, yeah, each programming language has a different pros and cons. Like for example, and C are like really hard to code for like people coming from non computer science background. So Python is a really good tool to start with, but often Python is a bit slow when we have to simulate all these kind of sophisticated equations and all the things, uh, we need more computational resources, and it takes like several long hours to calculate. So then yeah, it's best ways to work with simple codes like from Fortran or C++. So that's why I stick to C++ and work a bit on Python as well. So now there is a new language called Julia language, I guess, which is supposed to be faster, and it's still developing. I think I'm currently exploring it. Like, let's see how it goes.
Nice. Yeah, there's always going to be more better and better new languages would definitely evolve, making life easier for all of us. Knowledge of programming languages or using advanced software tools is only going to become more of a requirement and quite ubiquitous, right? For example, if you look at, I don't know, Excel, there's no job in the world right now that does not require Excel or some sort of processing of data and then manipulation of data. So that way, yeah, definitely pretty sure everybody would require to learn Python or some sort of that language in the next, I don't know, 5 to 10 years.
Yeah, it's like engineer's language programming.
Yeah, not only engineers, right? Like even, for example, I know one of my friends is a researcher. She's an environmental biologist, and her research is on. So she goes to places like Madagascar to do a lot of field research, and even she learns Python. She's learning Python now because she says it's her research has become so complex that it's easier for her to learn Python than to explain her research to a data analyst
Yeah,
to analyze her data. Yeah, that way it's very interesting. But yeah, Python seems to earn most of the brownie points because how easy it is to use, to learn to use. The barrier of entry is low.
for a person who doesn't have a background in programming and everything, yeah, you can learn it using a simple YouTube tutorial or something like that.
Exactly, exactly. And the end result is so satisfying, right? You can't generate those kind of beautiful images and graphs
Yeah,
in C++. plus plus.
even in C++, we have to use Python repository to have this kind of plots,
Exactly, exactly. Totally. Yeah, completely agree. Yeah, so how is Julia? So you mentioned this new language. How easy is it learning Julia? Is it as easy as Python? Because Julia is also more for it's for numerical methods and computations.
Yes, it's like kind of a language. Like it has a particular advantage, like it is fast as C and C++, and it we can program like Python. So that is the kind of advantage we get it with Julia. But the one issue is like still it is like a developing language, and I mean the community is so small, so it's slowly getting its popularity. So I think we have to wait few more years to see how it goes with Julian.
So you worked in a lot of places where there's a lot of hardcore research happening,
Yes.
and you are an engineer. So do you see any difference in how people with a research background and people with an engineering background see things differently or solve problems differently?
That's an interesting question. I would say, like, the research which I was involved completely, I mean, it involves like this kind of thinking, like how this physics goes inside this particular thing. For example, let's take the example of this blood flows problem. So I know I'm really quite knowledgeable in fluid mechanics, but my major challenge is to understand this biochemistry happening with the cells and these reactions happening inside the blood flow and this kind of medical probe, biomedical probes. So of course, I have to study biochemistry for that and understand how to solve these problems and everything. In For example, the same thing happens in physics also. I mean, for example, they formulate all these kind of equations and everything in much more deeper sense. Here, being an engineer, we may not formulate a equation or something. We just we do a lot of research. Okay, this is the formula tested on this kind of problem and this that. So we uh, we accumulate all this knowledge and we apply to this different challenges which we face in the engineering thing. Where in physicists, they work deeper into that kind of equation. So okay, what are the things? How can the equation could be improved, and what are the experiments which we need to do to prove this equation works and everything. So yeah, that is I mean, there is a kind of a bridge between engineers and physicists, but of course, yeah, it's physicists do in a much more deeper sense rather than engineers, I would say.
Nice, because they are equipped with all of the background knowledge and the insights into it so they can
Yes,
look
yes.
deeper. Again, I keep coming back to all your research areas because they're like so exciting. They're so varied. They're so diverse. I've never met anybody who's from a space background and having worked in so many diverse fields come to know of these research opportunities because like ships and medical research and particle physics is like completely different from each other.
I mean, regarding ships, because my parents, like my father works in like in a lab where like which also tests like ships and they do a lot of hydrodynamics. So I had the idea like, okay, these aerospace concepts can be applied in ship research as well. So I had this idea. So of course, I tried some opportunities in aerospace as well. At that point of time, like I tried opportunity in shipping industry as well. Like I also showed like, okay, I have some knowledge in shipping industry because I did some internships during my bachelor's in the shipping industry. So that's how I got the opportunities here in Swedish ship testing institute. Like keeping aside like the industry which I worked on, what I'm sticking to is like my concepts on fluid mechanics and this multi-phase flows and everything. It Of course it happens in the phenomena happens in this propellers in ships also, but the same phenomena occurs in some fuel injectors, for example, where I worked many years before starting this research in blood flow.
So you basically you need to seek them out by yourself. So my question is, do these opportunities come to you through your professor? Like, are people in these areas, let's say it's the head of this blood flow research, there's a project manager or there is a research head. Does that person think, hey, you know what, to do this research or to figure this out, we need somebody from an aerospace background or from a fluid dynamics background? Do they think about it, or is there somebody else like your professor or somebody who's connecting the dots? And right, so I'm just trying to understand how the connection is made between blood flow research and somebody like you who is absolutely not connected to the medical field in any way.
Of course, for example, the for the blood flow research, we are using an in-house code in the university, and of course, the person who has to work must have this knowledge in fluid mechanics, of course, and also he has to explore different things. But it's easy for them to hire a person with a fluid mechanics background to work on this project rather than a person of having biochemistry knowledge and then later train him with this fluid mechanics and everything. That's really hard, right? And being an engineers and we have taken a lot of this calculus courses and everything, it's easy for us to understand all this kind of complex mechanisms happening. So that's how people think and hire in your projects.
Okay, okay. Interesting, interesting. Also, one last question regarding this. We've drilled about it quite a bit, but just for my clarity. So, is it easier for people like aerospace engineers or people with aerospace background who are working in the academia and already doing research to get into this kind of interdisciplinary research, or is it the same even for somebody who's just an engineer working in the industry?
It's the same for everyone, I would say. It all depends on your knowledge background which you have. Like, for example, for example, you are an engineer working in aerospace industry, but you only have a knowledge of CAD and CAM. I mean, it's really hard for him to learn all this fluid mechanics and mechanics happening and everything. So since a person like me who's working completely into this mechanics, it could be structural engineering or fluid mechanics engineering. Yeah, the foundation should be strong. Whatever it is. So I mean, I would call myself like. Rather not an aerospace engineer, but I would call myself as like engineer who is having all this kind of knowledge. So I'm looking for a challenge. It could be particle physics, it could be space, it could be medical research or something. So it's like a hard challenge which people are posing to me, and I'm just solving it with my own knowledge. That's it.
Let's zoom out a little bit and look at the career path, right? So, typically for a researcher who's in the same field like you, because you started with your bachelor's in aerospace engineering and then you did your master's, and then you're pursuing a doctoral degree. You're doing research for a doctoral degree. So, after your PhD, how do you see your career path panning out? Do you see yourself in the industry? Do you see more opportunities in the academia? How do you think it would pan out?
Well, there are several opportunities in academia, and like I said, like I am an engineer having like well versed knowledge in like fluid mechanics or structural mechanics or something. So
And physics and blood flow and
mechanics,
ship testing.
whatever it is, but yeah, I mean, I would say like it's like a personal opinion, I would say, where you want to go. Some people get exhausted with doing all this research and just go to some like because they're exposed to all this kind of complex physics and everything. So they might work on some stock market, maybe like solving some Black-Scholes equation or something, or they know all this kind of HPC computing, so they could mine a Bitcoin or some cryptocurrency. There is, I mean, opportunities are various. I mean, it's your personal choice where you want to go. Like if you want to have work in industry with which, for example, if an industry is offering you like a really good amount of salary and everything, so you can go to research. But if you're so passionate to take your research to next level after your doctoral degree also, yeah, you will be working. Yeah, it's like a personal choice, I would say, where you want to go. But for example, there are like several opportunities. I mean, if I say I want to work with particularly in aerospace industry, then opportunities are less. But if I'm adaptable to different situations, like, yeah, you have several opportunities.
If you look at these opportunities and the geographic distribution of these, let's say if we consider space, most of the space activity has been happening in the US. Most of the like SpaceX and all these super cool, exciting companies. Even now, most of the space companies are in the US. Of course, Europe, it's slowly rising now. So that way, what do you think there are more opportunities for aerospace engineers? Not necessarily in space, but like you said, in any other fields that require basics in fluid mechanics and strong fundamentals. Do you see any particular geography having more opportunities compared to the other?
Well, I think space industry in India is improving because there are a lot of private space industries coming up. So that is one opportunity where someone can grab. And also like for example, I would suggest like all the people to work with open source technologies, because most of the these sophisticated projects will come up with this shoestring budget, so we can't afford all this kind of money, facilities, I mean, we can't pay everything. So once you are equipped with this, like once you are like you having a knowledge that you could develop and also do some R&D and improve. You can create facilities for yourself. I mean, I would say the opportunities could be enormous, I would say. So, like your question regarding the geography, I mean, you could start with, I mean, when you are like, it could be any country, I would say. It's not particularly restricted to India or Europe or yeah, anywhere in the world, I would say.
Yeah, yeah, it's good to know that there's a lot of opportunities everywhere around the world. So that's very nice to know. But so I'd like to come back a little more to your, take a further deep dive into the research that you've been doing. So you've explained quite a bit about the ship testing and what exactly that you're working on. Can we talk more about this biomedical research which you've done next? So what exactly was it that you were trying to accomplish with your research? What was the challenge? What value did you add to it? And perhaps you can also tell us about the status of that research right now.
Well, before diving into this thing, I have to explain the background of this project, like what happens inside a human body and everything. So, like it's a well-known fact, like 31% of the people in the world suffer with this cardiovascular diseases, like which we call heart attacks and heart failures and everything. So, one major reason for it, like cause for this one, is called atherosclerotic plaques, which happen in your blood veins, arteries or veins, I don't know exactly, but so what this plaques do, they inflammate this vessel walls of your veins, so they clog your blood vessels, and uh, they reduce the flow of blood to the heart, and also thereby reducing the oxygen flow level to the heart and slowly leading to a heart attack. So now, how do we test this? For example, for a person suffering like early stage of this cardiovascular disease, how do we test him? So one of the way is to test is like what happen. Like I would like to explain like what happens when this plague happens. So when this plague occurs in a vein, there is a layer called endothelium around the vessel walls of a blood of a vein, and this endothelium erodes. So they dissociate into small cells and they flow along with the blood. So these cells are called as circulating endothelial cells. So one way to test this disease is like we can inject some kind of isolating mechanism inside the human vein, and we can isolate the cells and we can count these cells. Okay, for example, you're having a really high count. What is your probability of getting this having this plague, or what is the probability of having a heart attack? We can quantify based on this count of this endothelial cells. So this is the background of this project. So now there is a startup here in Berlin, which was particularly designing this kind of biomedical probes that could isolate these endothelial cells, basically. So it's and for, I mean, they're testing on they are having different experimental setups for it, and they're testing on themselves, basically. Like they have to isolate this probe for like 1 hour or 2 hours to isolate all these things. It's a longer time. No one is would be happy to insert a probe inside your vein for like several half an hour or 1 or 2 hours. So, and like I mentioned before also, like I mean, I mean, the experiments are not really open like how we do it in industry. I mean, it's very unethical to use human blood and these human cells and everything. So, what is the easiest way to do is like to create a mathematical model for it, create a simulation, and also introduce this model of this probe inside our numerical setup, so we can design this probe from our calculations. Okay, this kind of so we design a random probe design, and we introduce in our numerical model. Okay, this probe can now isolate more number of cells than the previous design, so we can optimize the design. And also we can also arrive at a design which is like okay, if we use this particular probe design, we can isolate within less than half an hour. So how cool is that? So the major challenge is, like, of course we had to simulate the blood flow. So we have a fluid mechanics software, and okay, which does that. And like I said, blood is non-Newtonian fluid. Uh, so we can apply this model. We are trained to use all this kind of codes. So now the major challenge is, like, the blood has to carry this endothelial cells. So already people are doing, like, this particle transport applied in this, for example, in oceanography, or like the sewage drains. There will be a lot of garbage floating inside our place. Okay, so they couple different methods called discrete element method and fluid mechanics. So I was using the same method. Like, I assumed the endothelial cell to be some kind of impurity or a sand granule particle inside a pipe or something. So another major challenge is this endothelial cells have a reactivity. So this basically what this how this biomedical probe isolate the cells is, like, it is coated with an antibody which can attract the cell and capture the cell. So it's and from the experiment it's evident that this kind of binding and is like kind of a stochastic process. So we don't have a deterministic way to predict this phenomenon. So I was using this stochastic mechanism, all this theory, probability, population growth, and decay theories, and to arrive at the formula that could um, relate this hydrodynamic force with attachment and detachment kinetics. So I could do that. So now there is another challenge. So there are, like, several constants which I need to know, so that I can implement this model into my numerical framework. So we had to design some experiments for that uh, to find these chemical properties of happening with the cells and antibody. So we did that, and we found those kinetics, and we implemented in the numerical thing framework. And we we thought of that it could predict really good results using this model, and indeed it predicted really good. Like, I showed you this picture like few weeks ago. uh, yeah, it is predicting quite well, and now with this tool can be used. It can reduce, like, several experiments. And yeah, they can, for example, they want to, now they're experimenting with similar blood fluid similar to blood called dextran. So now they can directly, with this simulation framework, they can simulate with the blood properties directly, and also they can use this endothelial cell properties and everything. So yeah, this is how the numerical simulations work in the medical industry. For example, I know a person who is working with this inhalable drugs delivery with the fluid mechanics. So the fluid flow, there is a fluid flow from nostril to lungs, of course. And then there is these particles are like the drugs. For example, uh, just a second. For example, I mean, who would be ready to, like, for to inhale some radioactive samples, so that I can make an X-ray out of you, so to see, like, whether the sample delivery is going right or wrong.
Yeah.
So one of the best ways to do all these kind of simulations. So in aerospace, like I said, like in aerospace, we do all this kind of complex stuff. So we just applying into medical research. So it would help, like, all this biomedical research people to create all these kind of new instruments that could solve this problems in this medical industry, basically.
Interesting. Nice, nice. Cool. Very interesting. So essentially, people with a background in fluid dynamics are the ones who will be, contributing to these kind of research and these kind of projects.
Not only fluid mechanics, even structural as well, because for example, we have this stent. uh, so that will they have to do a lot of research with this material, of course, materials engineering, and a lot of stress strain relationship with this, how this, I mean, there is a compression, decompression, everything. So basically, mechanics is the key, I would say. And also electronics, people who like having your background. Yeah.
Yeah, yeah, that's very great to know. Nice. Cool. So this is about your research at Charity on the biochemistry and the blood flow research. And can we perhaps elaborate on the DESI, the particle lab research that you've been doing?
The thing which I'm working currently is called single particle diffractive imaging. So where we sample all these nanoparticles, and we basically what we do is like we extract the structure of this nanoscale particles, by imaging by heating up with laser, and it creates a diffraction pattern, and we study this diffraction pattern, and we create this 3D structure based on this data which is available. For this sample delivery, again, we need fluid mechanics. We use typical injectors for it to do this. Like, so the injectors collimate these beams to increase the hit rate between laser and these particles. This setup includes some different. Sometimes there'll be microscale heat transfer involved in these injectors, and there are like several flow regimes, like from for example, the injection pressure could be from atmospheric pressure to for example, to ultra high vacuum. So regime changes. For example, I use what in fluid usual fluid mechanics. What we use is called a Navier-Stokes equation. For example, I can't use this Navier-Stokes equation in a ultra high vacuum. So there I have to use some other equation called Boltzmann equation and other theories. So basically what I do is like I couple these different methods and make a new simulation tool that could predict all these flows. For this, I am also collaborating with other researchers who are working in this re-entry vehicles, who are working in this hypersonic re-entry vehicles, because this kind of same phenomena occurs in our re-entry, atmospheric re-entry, where the flow transits from ultra vacuum to slowly into ionic, then it goes to the pressure increases from ultra high vacuum to atmospheric pressure there as well. So
That's very interesting. Very interesting. If there are so many parallels, if there is so much overlap between the concepts and the knowledge between aerospace engineering and a lot of these diverse areas, and the aerospace engineering is a lot of research that goes on in aerospace engineering is very closely guarded because of its nature. It's very strategic, it's high technology, nobody wants to really put it out in the open. Do you think we would have benefited much more if people who have worked on a lot of this aerospace research have put it out in the open, make it open, more open source, so the other fields can take this ready-made knowledge?
well, there are several examples. For example, in Indian space, I think it's mentioned in one of the autobiographies of Abdul Kalam, where he was working on uh, very light materials called composites, which are used in these rockets and missiles, basically. And he visited a doctor, and the doctor examined these materials, and he gave an idea like, why can't we use these materials for making calipers, all the crippled children. And slowly the laboratories developed these calipers, and they have given to the children who are, especially if they are wearing like heavy calipers, they started running all of a sudden. So this where like engineers need to network with other people with other areas, that would give new ideas. And also I know like uh, one of my colleague from my university where I did my masters, like she is also into fluid mechanics. She is also working with blood flows and everything, and she is doing a side project like developing like biodegradable sanitary napkins for women's health. And she used the fluid mechanics and this porous media concepts to like basically creating this kind of numerical framework. And she's testing all these different materials, and how they can design this kind of napkins and other stuff. So yeah, uh, that's the thing which I would say, that's really the here you can see the importance of women in this kind of field. It's very unusual for a man to get such kind of ideas. So yeah, basically I would say like interact with other people, like not only medical people, it's also people from agriculture, from people from like yeah, for example, Wall Street or anything. So your concepts could be applied anywhere. So
Yeah, yeah, that's great to know because mostly when we think of spin-offs, a lot of there are a lot of spin-offs, right? There's a lot of spin-offs from the space sector into non-space sectors, but most of these efforts have been spearled by space agencies like NASA or also in India, ISRO, and probably the European Space Agency. But it's really nice to know that it's also happening at the researcher at the grassroots level, the person who's actually working, the engineer, the researcher who's actually working on this research reaching out to people in the other sectors and trying to bridge the gap. So that's very good to know.
and one more thing, also, like I need to appreciate your work. You are balancing your scientific work and also doing this podcast. It's not like, yeah, it's really amazing, I would say.
Yeah, you're very kind, but I believe that I'm getting more out of it than I'm giving out because usually I'm in a very small. I'm an embedded engineer, like so I'm in a very small bubble. So this way, when I get to speak with people like you, I learn so many other concepts because all the terms you were mentioning, like the stochastic flow and what was that flow equation, all these Boltzmann constants. Oh, these were something that I studied. Oh God, maybe more than 10 years ago, and it's like slowly coming back. So it's very interesting. And yeah, every time I should tell you that every time I speak to you, after I speak to you, I spend a couple of hours brushing up my basics and then googling everything that you said, and then I was like, oh, this is what he meant. So yeah, it's been a fabulous, fantastic conversation as always. Hope we can have another conversation. Hope we can keep having more conversations as you keep doing amazing stuff. And I'll get back to you again once you finished your research at DESI,
Yeah, sure.
and maybe we can talk about it. Yeah, thanks for your time. As always, it's been super fun.
Thank you very much.